Okay, so before we start tonight's lecture, which is continuing beam design, before we get into tonight's lecture, does anybody have any questions they would like to ask me about the homework or what we've done so far?
So for the homework, are you gonna post like an answer key on Blackboard or?
Yes, that is my intention.
Okay.
I have basically like hand calced out solutions for these problems. And so it is my intention that I will post them to Blackboard probably tomorrow.
Okay. And Professor, so like the tests, like for the test, with like going over the problems, homework problems would be very similar to what is on the test, right?
Yes,
Okay.
yes. Generally, my tests reflect the homework pretty closely.
Okay.
It reflects what's in the textbook, and they reflect what's we are doing in my example problems and what we're doing in the lectures.
Right.
But I think one of the best ways to prepare yourself for the exams is to not just do the homeworks, but struggle with the homework somewhat and kind of work through them and develop your skills for solving those types of problems.
Right. Okay.
Okay, does anybody else have any questions they'd like to ask before we get started? Okay, hearing none, then we're going to start with tonight's presentation. This is going to kind of dive into beam design. What we've done so far is, as I explained before, is really kind of more just beam analysis. And tonight we're going to go into beam design. Okay, so first though, I want to get into load and resistance factors. We've been talking about these for 3 lectures now, but I want to give you a somewhat abridged or a summary version of what are load and resistance factors. Okay, so if we look at a distribution of the load and we look at a distribution of the resistance, so Q is your demand and R is your capacity. So if you anticipate your load demand to be Q, then there's a statistical spread of what the load will really be. And remember from statistics, you have standard deviations. So one standard deviation on either side of your norm or your median is something like 33% is on this side and 33% is on this side. And within 2 standard deviations, you've captured something like 95%. But there is always a probability, there's always a chance that you could have an anomaly on the load that is outside of a standard deviation. And so load factors and resistance factors are based on statistical probabilities. Sources of load that are well-defined, dead load, have a small load factor than do the load sources that are poorly defined, like a live load. Structural capacities that are well understood, reliable, and ductile in nature, flexural bending, have higher resistance factors than those that are poorly understood and can lead to sudden or brittle failures, like a column compression or concrete in shear. Okay, so back to what we're doing here. You could estimate that the load demand is Q, and it may be lower than Q in reality, or it may actually be a bit higher in Q in reality, but it's probably not going to be too much higher. The odds, the probability is that your load is not going to be twice as much load as you thought it would be, but there's some probability as to how much more that structure could see in its lifetime than what you assumed. And like we said, dead loads it's very, very unlikely that you're going to misjudge the dead load of a building by even 150%. But it could be likely that you misjudge the live load on your building by 150%. So
And
this is
Professor,
the,
why does that usually happen?
I'm
Like,
sorry, go ahead.
why do we miss like find the life load?
Okay, I'll give you an example. Let me bring up, there we are, and okay, there we go. I'll give you an example of a misjudged live load. And please understand, this is not anybody's fault. It's just the nature of the live load.
Okay.
So the Golden Gate Bridge, San Francisco Bay, spanning from San Francisco to Marin County, the Golden Gate Bridge was designed in the late 20s or early 1930s. And my understanding is back then they didn't have well-defined codes and prescriptions and that sort of thing. So the designers of the Golden Gate Bridge decided that they're going to take the heaviest dump truck that was on the road in the late 1920s, load it up with rock, and they're going to put these dump trucks on the Golden Gate Bridge, bumper to bumper, doorknob to doorknob, from one end to the other. And they said, this is the absolute worst load this bridge is ever going to see. And that's what they designed it to. Not too long ago, the Golden Gate Bridge celebrated its 75th anniversary. For the 75th anniversary of the Golden Gate Bridge, somebody decided, why don't we, on a Sunday morning, shut down the traffic and just open up the bridge to all San Franciscans to walk across the bridge and enjoy the bridge? That's a wonderful idea. Okay, let's do that. So they shut down the bridge on a Sunday morning, and they made a big ad campaign, and everybody come out on the bridge, enjoy the bridge. This is your bridge, come enjoy it. And they had quite a turnout. So people were walking across the bridge, starting in San Francisco and ending up in Marin County. And as the people are going across this bridge, somebody noticed that, doesn't the bridge normally have like a curve to it that curves up at the middle?
Right.
There's no curve to the bridge today. Somebody noticed that this bridge had dropped about 8 feet in the middle of the bridge. And then they said, oh boy, did anybody figure out how much all these people weigh? No, didn't really think about that. So they quietly put some road closed signs on the San Francisco side and just let everybody who had started on San Francisco finish walking out to Marin, and quietly, calmly just waited for everybody to get off the bridge. What they didn't realize is that they had like over 800 and something thousand people on that bridge, and they weighed a lot more than those dump trucks.
Okay, yeah.
That's my bridge story. Another example that happened in the news fairly recently was apparently there's this new thing out there called social media. I'm just now becoming aware of it, but apparently there's this thing called Facebook or Twitter, or I don't know what these things are, but apparently if somebody wants to throw a party, they can tell 1 or 2 million of their closest friends to come to a certain address and have a party. So apparently 1 or 2 million of these people's closest friends came out to this house, and these people packed the house with people, elbow to elbow people in this whole house. And what they didn't understand or realize was that the ground floor of the house had a basement underneath it. And these people were roughly about 2.5 times heavier than the designer of that house had ever figured on. Basically, you design a house, you're designing to 40 pounds a square foot. And these people were pushing about 120, 150 pounds
Oh,
a
wow.
square foot. So the whole ground floor collapsed and everybody fell into the basement. Nobody was hurt because they were all drunk, you know, so it was okay. But that's another example of I'm the engineer. I think this is my load. And when I designed this house, nobody even thought of such a thing as Twitter, but Twitter caused a load over here. And so there are probabilities that are unexpected. By the same token, when I design something, or if I design a column or a beam or whatever it is I'm designing, I design it to have a nominal capacity, right? Part of your homework was to come up with the nominal capacity of a concrete beam. The nominal capacity is right where I say this R is. That's the mean of what the nominal capacity should be. But that beam may actually end up being stronger or weaker than what I assumed it to be. It may end up being stronger because maybe I wanted 4,000 PSI concrete and what I actually got was closer to 6,000. That would make it stronger. Maybe I assumed a rebar will yield at 60 KSI and it actually didn't yield or doesn't yield until 72, 74 KSI. That would make the beam stronger. But let's say that I called for the steel to be 2.5 inches from the bottom of the beam, and they actually built it 5 inches from the bottom of the beam. That would make it quite a bit weaker. What if I wanted the beam to be 36 inches deep? They actually built it to be 33 inches deep. That would make it weaker. There's all kinds of misunderstandings or mistakes, typos, just flat out human error that could cause this to be weaker than we had assumed. And it could be material properties. Maybe I wanted 4,000. Instead of getting 6,000, I actually got 3,500 PSI. That could happen. So there's all kinds of reasons why the actual beam may be stronger or weaker than what I had thought. So here's the point of the whole thing. If concurrently the load is so much higher than what I had assumed it to be, at the same time that the beam is weaker than I had assumed it to be, then anywhere that these two overlap, if you actually got into a situation where these overlap, what does that mean? What's the consequence of overlap?
Is it failure?
Is it failure?
Absolutely right. That means you have a failure. It means that at the same time, defying probability, the load was higher than you thought and the capacity was lower than you thought, and these two overlap, then you have a failure situation. And it has happened. There's been quite a few documented failures in the world of structures, so it does happen. So what, as designers, what do we do to try to prevent that? So the whole scheme of load and resistance factors is that I take the load that I think I'm going to have and I amplify it by a load factor. I take the nominal capacity that I think I'm going to have and I reduce it by a resistance factor. And as long as, bear with me, let me get the right pin here. As long as after you have amplified your load to this point and you have penalized or decreased your capacity by a resistance factor to this point, as long as this is still greater than this and there's no overlap, then statistically speaking, you should be safe. That's the whole point. So I take my loads, I amplify them. I take my capacity and I decrease it by a resistance factor. And then I compare the two. And as long as my decreased capacity is still greater than my amplified load, then we are okay, where we have a safe design. Now, that's not to say that you can never have a failure. It just means that statistically speaking, the likelihood of a failure is acceptably small. You never get to 100%. It's statistically impossible to ever get to 100% of anything, but you can get really close. And so we can feel confident, we can sleep at night. We've done our job to protect the public, that we have gotten really close to being sure there won't be a failure, but it's not impossible. Okay, so does that make sense? And this diagram really is here to illustrate why we have a load factor, why we have a resistance factor. That's what this is for. And it's also here to show the difference between the likelihood of an overload of dead load is much smaller than the likelihood of an overload of live load. Both of those examples that I gave you, the trucks and the people on the bridge and the people in the house, was a gross overloading of live load. The bridge didn't get any heavier. The house didn't get any heavier. It was just the number of people that they put on these things that got heavier. Okay, so does that make sense? Do I have any questions on this? Okay. Okay, so ACI 318, section 5.3.1 and table 5.3.1 give the required load combinations as, and we're going to have several here. You have 1.4 dead, 1.2 dead plus 1.6 live plus a half of roof live load, snow, or rain. Or we can switch them. 1.2 dead and 1.6 roof live load or snow or rain, or 1.0 live load or half of wind. W stands for wind. Or we can have 1.2 dead plus 1.0 wind plus 1.0 live plus a half of roof live load, snow, or rain. We can have 1.2 dead plus 1.0 earthquake plus 1.0 live plus 0.2 snow. 0.9 dead plus 1.0 wind, or 0.9 dead plus 1.0 earthquake. These are the basic load combinations. I'm sorry?
U stands for the load combination, right?
U stands for ultimate.
Okay.
So this is generic. This is very generic. Okay. If I'm talking about moments, then this would be M sub U, and this would be MD. If I was talking about column axial load, this would PU, PD.
Okay.
Okay, so these are just very generic for whatever action we're talking about. Yes, these are the same as you would find in ASCE 7. Yes. Where U is the factored load effect, U may represent bending, M sub U, shear, V sub U, torsion, T sub U, axial compression, P sub U, etc. Okay, and here's some definitions of each one of these components. Before I do that though, why do we have to have, what do we have here? 7 load combinations. And there's actually more. There's more than 7. There's like little sub combinations that go into these. Why? Why do I have to have so many load combinations? Well, it's all about statistics. So the simplest way to explain it is, what is the probability? What is the likelihood that you're going to have the greatest wind effect that you would see in 100 years on the same day as you get a magnitude 7.0 earthquake? What are the odds of that? Well, slim to none. Very, very, very low. So you will notice that there is no load combination that has earthquake or wind in the same combination. That's just unreasonably improbable to even include those two in the same combination. What is the likelihood that you have what is the likelihood that you have too many people on the same day as a windstorm? So we decided to let 800,000 people onto the Golden Gate Bridge. Oh, and by the way, we got a hurricane coming in from Hawaii. Pretty low. So the 1.6 on the live load is to capture that live load is very difficult to get your hands around. And at any given time, somebody might post a party on Twitter and you have 500 people in your house. That's the 1.6. But you're not going to have that at the same time as a hurricane. I mean, how many people are partying in the middle of a hurricane? You might have an earthquake in the middle of a kegger, but what are the odds? And as soon as the ground starts shaking, all the drunk people fall out of the house anyway. So not very likely. So that is the nature of this. The nature of this is that you might have a snow load, S, that exceeds what you were expecting by 60%, but you're not going to have that snow load at the same time as too many people on the structure. Or this doesn't really make sense. Why is this or? Well, you're not going to have too many people on the roof when the roof's covered in 10 feet of snow. And if you have 10 feet of snow on the roof, you're not going to have any ponding or rain load on the roof at the same time. That's why these are ors. You're not going to have any of these three at the same time. So that's the nature of the combinations. They're trying to capture some things would be disastrous if you had too much of it, but you're not going to have too much of this and this and this at the same time. That's the idea. These last two recognize that you could have situations where the dead load of the building actually helps hold the building down. If you have a wind that's trying to push the building over, then the weight of the building itself is really what's holding the building from being pushed over. So if that's the case, we're not going to take 1.2 times the weight of the building because you might have actually overestimated the building. So that's why we have 0.9 times the weight of the building, just in case the building's a bit lighter than was estimated, because the weight is helping you against the wind. And the same could be true for seismic. Okay, so does this brief summary of load combinations, does that make sense? Do I have any questions? Okay, so let's talk about some of the definitions. D stands for dead load. Dead load is the self-weight of the structure and any permanent attached architectural components, mechanical units, plumbing, electrical, etc. This would include solar panels if they're bolted down. This would include siding or glazing, anything that's really a part of the building. But this generally does not include furniture. Cabinets or furniture, even your refrigerator, that's considered live load, because if somebody can just move it all out and move in their own stuff, like in an office, if you lose a tenant, everything moves out, and then the new tenant, everything comes back in, so that's live load. Live load. Load effect to account for transient loading of structure, including occupants, furniture, traffic, etc. Live loads are prescribed by ASCE 7. Live loads may be reduced per ASCE 7 Chapter 4. So live loads are really beyond the scope of structural engineers making them up. it really takes a lot of statistical studies and a lot of historical evidence as to whether or not you have enough live load to design the structure properly. A good case in point is parking garages. We design a lot of parking garages, and I remember a day when the load in a parking garage was 50 pounds per square foot. Now, 50 pounds per square foot may not sound like a lot when a given cars usually weigh somewhere between 3,200 and upwards to over 6,000 pounds, even maybe over 7,000 pounds for all of those who have the full-size Dodge Dualies. Those are really heavy trucks. But even the heavy F-250, Ford, Dodge, whatever, big pickup trucks, the thing is, they're heavy, but they take up a lot of space. How many square feet does a full-size truck take up? It's actually quite a bit. So when you take a full-size truck and divide it by its footprint, its actual weight is more like about 30 pounds a square foot. Take a car, any size car, it's lighter, but it occupies a smaller footprint. So it averages about 30, 35 pounds a square foot as well. So 50 was actually too much. And back in the day, we used to reduce that. This live load may be reduced thing. We're able to reduce 50 pounds a square foot down to about 30 pounds a square foot for parking garages. Today, they've changed that to be 40 pounds a square foot unreducible. So that's it, 40 pounds a square foot, that's what you design to. And after doing parking garages, not me personally, but we've been doing parking garages for 75 years now, it's been deemed that 40 pounds a square foot is an acceptable design, and nobody's seeing any kind of failures in parking garages. So my point is, that's all done by ASCE 7. They're the body that has the resources and the research to figure out if these loads are adequate for what we're trying to do. Live loads may be reduced. Okay, well, think about this one for a minute. Think about a parking garage that you may have been in recently. And if you're designing a concrete beam that's picking up some tributary on both sides of the beam, it's still pretty unlikely that the entire tributary of that beam is going to be covered in cars. Again, bumper to bumper, doorknob to doorknob. It's kind of unlikely that the whole tributary is going to be smothered in cars. There's always spaces between the cars, particularly drive aisles. There's always space down the drive aisle. Even more so, think about the tributary to a concrete column in a parking garage. There's actually a lot of free space for all the area that column is picking up. So the code recognizes that it's the bigger the tributary area is, the less likely that every square foot of it is going to be occupied by the design load. So that's what the reduction is about. We're not going to work or touch on that much more than what we're talking about here. For the most part, this class, I got to get this back on focus to concrete design, but just be aware that this is where it's coming from. Roof live load. Load effect to account for transient loading or maintenance personnel or other transient roof loads, planters, etc. Prescribed by ASCE 7, roof live loads may be reduced per ASCE 7 Chapter 4. Snow load. Snow load is a semi-transient load due to snow. Does not apply in all locations, but in some locations can be the primary load effect for roof structures. Procedure to determine snow loads found in Chapter 7 of ASCE 7. So just for example, again, I mentioned we do a lot of parking garages, and all of our parking garages we design for 40 pounds per square foot. We did a parking garage in South Lake Tahoe. The parking load was inconsequential to the snow load. In South Lake Tahoe, I had to design that roof deck for 150 pounds a square foot due to the snow, which was many times higher than the load due to cars. R stands for rain load. Rain load is prescribed by Chapter 8 of ASCE 7, primarily required for ponding checks. Yeah, rain isn't really a load, but if your drains get clogged up and you start backing up water and you start getting 3, 4, 5 inches of water on a deck, that's a load. That's a real load. And if you look back through, like maybe the Engineering News Record, the magazine that documents construction, like 9 out of 10 structural failures across the country were ponding failures. They were light wood roofs that were flat. Think of like all the tilt-up construction warehouses that we have around here. Well, those roofs are very light steel trusses or wood roofs, and they're flat. So if those drains back up, it does not take a lot of water to fail one of those roofs. So this can be serious. Wind load effect to account for transient loading from wind. W is primarily a lateral load, but can cause uplift due to negative pressure. Lateral force resisting systems must be designed for shear, overturning, moments, and uplift on the system. Wind is prescribed by ASCE 7, chapters 26 through 31, and is way beyond the scope of this class. That is, they've made it pretty complicated at this point. E stands for earthquakes, something near and dear to all of us here in SoCal. Load effect to account for transient loading from earthquakes. E is primarily a lateral load, but also has a vertical component that can affect structural members not part of the lateral force resisting system. Earthquake loading is prescribed by ASCE 7, chapters 11 through 23. Other sources of load. T is restraint. Load effect to account for structural restraint from volume change, shrinkage, and temperature, and differential settlement. Prescribed by ASCE 318-536 and ASCE 7234. Fluid load. Load to account for the weight or pressure of fluids on the structure. And I'm not gonna, I think you guys can review. I've put this on Blackboard, so you can review. I think we're falling behind a little bit on time. So all of these references, you can go back and double check. H stands for lateral earth pressure, load effect to account for lateral pressure exerted by soil loading, prescribed by ACI and ASCE 7. Thinking of retaining walls. This would be the main structural element that you see all the time that has lateral earth pressure, would be retaining walls. F sub A is a flood load effect due to flooding, prescribed by ACI and ASCE 7. Wind on ice. I don't think this is something we really worry about too much, but the account for atmospheric icing prescribed by ACI and ASCE 7. This is kind of a weird one, This is when you get an ice storm and there's enough humidity in the air, but it's below freezing, so everything freezes over in these gigantic icicles over everything, and then the wind hits the ice and knocks everything over. Seismic load effect, E, is actually 2 parts, E sub vertical and E for horizontal, to account for vertical and horizontal accelerations. The horizontal is dictated by ASCE 7, chapters 11 and 12, and is resisted by the lateral force resisting system, usually in concrete structures as shear walls and moment frames. The design of shear walls and moment frames is outside the scope of this class, and so E sub H will not be looked at this time. So you think, we're off the hook. We don't have to worry about seismic. Not so. E sub V is the vertical acceleration due to seismic, and it is applied to the lateral force system as well as to the gravity-only system. So you could have concrete members that have nothing to do with the lateral force resisting system that's resisting earthquakes, but because the ground accelerates vertically as well as horizontally, it becomes one of our load combinations that we have to check virtually on every product that we do. ESA V is prescribed by ASCE 712422 as 0.2 SDS-D, where S sub ds, SDS, is the design spectral acceleration parameter given by ASCE 71145. This value is required to be calculated and reported on the structural drawings. So all projects across the United States, the structural drawings have to have the SDS factor on the cover sheet someplace, unless you happen to be in one of those states that just said, oh, we're not going to worry about it. And as far as I know, Minnesota is the only state that I've come across that said we're not even going to write it into the codes. Every other state, from low seismic risk all the way to the highest seismic risk, this SDS factor has to be found and reported on the cover sheet. If needed for this class, I will provide it for you. If ESA V is substituted back into the design combinations, then you get this new combination. U is 1.2 plus 0.2 SDS times the dead load plus 1 times the live load plus 0.2 times the snow. Or the other one is 0.9 minus 0.2 SDS times D. And this one, that can really hurt you if the weight of the structure, you're counting on it to help you. So 90% becomes, this could be as low as in the 60s, like 65% for uplift. Thus, for concrete design and the purposes of this class, the controlling load factors generally are 1.4 dead, 1.2 dead plus 1.6 live, or 1.2 plus 0.2 SDS dead, 1.0 times live. If the loads are given as U loads, MU, VU, etc., then the loads are factored. If loads are given as something something D plus something something L, for example, then these loads must be factored for strength design or left as service loads for service checks, deflection, cracking, as will be covered later. Okay, feel like I did a lot of talking. Does anybody have any questions about load factors?
It's not questions. I guess we just have to save them in applications. Like we're reading the numbers and the formulas, but when we see them in applications, it'll be easier.
Okay, point well taken. And we'll do some examples. I guess the takeaway from this is that you have to evaluate at least the 3 that I just gave you. You have to evaluate the 3 different combinations, and whichever combination gives you the greatest demand, that becomes your controlling case, and that becomes your demand. And then you go on to calculate your capacity and you compare them. Okay, so let's talk about capacity, the other side of the equation. So we have these resistance factors. This is Greek letter phi. So whenever we talk about this, we just say phi mn, phi vn, that sort of thing. Well, that's phi. Phi is the resistance factor. Phi is used to account for defects in material strengths, defects in workmanship, consequences of failure. If a beam were to deflect too much, is a totally different consequence than if a column completely crushed and collapsed, as obvious to anybody. So the consequences of the failure also play into the phi factor. Phi factors are prescribed by ACI 318, Chapter 21, and Table 21.2.1. Moment, axial force, or a combined moment or axial force the phi actually varies between a low of 0.65 for compression controlled up to 0.9 for tension controlled. That is based on epsilon sub t. If epsilon sub t is less than 0.005, then phi is this linear expression for what's known as the transition zone, where epsilon ty is Fy over E sub s. So this is the yielding strain. That's what that is. So you calculate epsilon sub t like you just did for homework problem number 2. And then you plug in, if epsilon sub t is less than 0.005, you plug it in, you put in the yielding strain, and this cranks out a phi factor. If epsilon sub t is greater than or equal to 0.005, then phi is just 0.90. And anything greater than 0.005 is tension controlled. Phi is equal to 0.9. Additionally, for pre-stress members, phi will vary linearly with strand development at the ends of the member, just so you know. For shear, phi is 0.75. Torsion, 0.75. For bearing, 0.65, because the failure mode basically for bearing is crushing of concrete. Post-tension anchorage zones, 0.85. Corbels, 0.75. Strut and tie designs, which are outside the scope of this class, but they would be 0.75. And ductile connections of precast, like welding rebar to rebar, is 0.9. Plain concrete is 0.6. Anchors into concrete will vary from 0.45 to 0.75 given the conditions. Oh, I guess that was it. Yeah, we covered the columns. Okay, so ACI 318-2124 modifies the phi value for special moment frames, special structural walls, shear walls, and intermediate precast structural walls. ACI 21241 modifies the phi factor for shear to 0.6 for any member designed to resist seismic loads if the nominal shear strength is less than required to develop the nominal moment strength. Again, outside the scope of this class, this is dealing with seismic resisting systems. And ACI 21242 modifies the phi value for shear for diaphragms to the least value used for shear the lateral force resisting system. I kind of just included these so that you can use this as a reference, but all of these deal with seismic. And again, seismic modifies the phi value for shear to 0.85 for diagonally reinforced coupling beams. Okay, let's see, design of rectangular beams, analysis of beams. Did I have any questions about phi factors? Okay. The analysis of beams determine the capacity of a beam where all design elements are known, including, you know, the strength of the concrete, you know, the strength of the steel, F sub Y, you know, the depth, H or D, you know, the width, you know, the area of steel. So if you know all of these are defined, then what you're doing is an analysis of the beam to find your capacity. If you don't know all of these, then what you're doing is a design of beams. When all the design elements are not known, you determine the design values for the missing elements. If only one design element is missing, then one unique solution exists and can be solved for. The most common is you don't know how much steel you need. That's the most common design problem. So all of these parameters are given. You need to find how much steel you need. If more than one design element is missing, as it usually is in the real world, then infinite solutions may exist. guides and or rules of thumb must be used to reduce the unknowns. The example of this is uh, you need to span 30 feet. You need to carry so many kips per lineal foot. You need to come up with a concrete beam that will span the 30 feet and safely carry that kind of load. Well, you could come up with a fairly shallow beam that has a lot of steel in it, or you could come up with a really deep beam that has minimum steel in it, or any beam design in between. There's an infinite number of solutions to that design problem. So usually what happens in the real world is architecturally, you'll have a limit on how deep you can go. So architecturally, they say, well, the beam has to be 3 feet or less, because if it's more than 3 feet, I don't have enough story height. I can't drive my car underneath it, or I don't meet code for ceiling heights or something to that effect. So generally, your answer comes from other sources, architecturally or something else. So, but we do have some rules of thumb. The height of the beam that you're going to need can be approximated by ACI 318, section 9311, and table 9311. The beam width minimum can be approximated by the textbook table 8.5. And now that we've done one homework problem where you calculated the required width of the beam by hand, from now on, you can just refer to table 8.5 for minimum beam width. Beam depth can be approximated as 1.5 to 2 times the beam width. They can be narrower for deeper beams, but this is a place to start. Beam depth generally is specified in 1 to 2 inch increments. Beam widths are generally specified in 2 to 3 inch increments. And that's common sense. You're not going to go out there and tell them to build a beam that's going to be 13 and 5/8 inch wide. You're going to, generally speaking, beams are going to be 10 inches wide, 12 inches wide, 14 inches wide, that sort of thing. I have a question that asks, is the beam height, width, and depth dependent on the location of the beam in the structure? It can be. They can be. Your limitations are more likely going to be dependent on the location of the beam in the structure. Hopefully I'm touching on this. Many times, let's go back to a parking garage. Many times in a parking garage, I need to span the beam 36 feet. And it needs to be able to carry a certain amount of load, 6, 7 kips per lineal foot. And the width of the beam is going to be dictated by the forms. Whoever's building the building, they're going to have some forms that are made up, and they're not going to want to custom make all the forms. So they're going to want to use the forms that they already have. We have forms that are 2 feet wide. So the beam width is already established because we're the contractor and we want to use our 24-inch beams. The depth is going to be dictated by the architect has established that the floor-to-floor height, say, is going to be 10'6". And the code requires that you need 7'2" clear to drive your car through. So if you do the math, that gives you how deep the beam can be. But again, maybe we have pre-made forms that use a beam depth that's less than what it can be. So there's a zillion, gajillion different variables that go into this. That's why you have to have more information. You have to have some rules of thumb or some guides. Or we can try to design our beams based on a reinforcement ratio rho that can be approximated by a desired target. And this would be given to you. You don't invent this. But one such target, a common target, is that rho should equal about 0.18 f prime c over fy, or you may want to set as a target that your epsilon sub t is greater than 0.0075. Remember, 0.005 is a minimum on epsilon sub t. You want to target for something that's above the minimum, something more comfortable. And so again, these would be given to you if this is what the target should be. Equations that relate rho and Rn equal to mu over phi bd squared can be used to find required steel area once a depth and width can be approximated. So you use whatever is given to approximate a depth and a width. Once you have those, then you use these tools to find the required area of steel. Okay, any questions on that section? Okay. Design of rectangular beams. In the back of your textbook, you have these tables 8.8 to 8.13. And these tables basically are relating R sub n to rho. And you can work them backwards and forwards. You can solve for what R sub n needs to be and then look up rho, or vice versa. Or you can use the equations. The equation is R sub n is equal to mu over phi bd squared. This is not a measure of nature. This is just an index. This is a man-made index to basically describe the load over the area of concrete that you have. And so it's just easier to use this index and rather than calculating this all the time. So R sub n is equal to rho Fy 1 minus 0.59 rho Fy over F prime C. So this equation is relating R sub n to rho. If you solve for rho, then what you get is 0.85 F prime C over Fy 1 minus square root 1 minus 2Rn 0.85 F prime C. Okay, so if you have enough information to solve for R sub n, then you can get rho. Or if you have enough information for rho, then you can solve for R sub n. And those tables, 8.8 to 8.13, just do exactly this. They're just relating back and forth. Okay, who's ready for an example? Who's still awake?
I'm ready for an example.
Yay, all right, somebody's still awake. So here's my beam. This beam is 9 inches wide and 18 inches deep, 16 inches to the center of the steel, which of course means you have 2 inches to the bottom of the beam. The given is the dead load is 26.7 kip feet. The live load is 44.2 kip feet. And we have an SDS factor of 1.45, which is very, very normal around here in the LA basin. I'm giving you that the strength of concrete is 4,000 PSI, the steel is 60 KSI, and what I want from you is find the required steel to satisfy the demand of the load. So here's a problem where everything is given to you except the area of steel. That's the only thing missing. Solution. Well, first we have to find the factored load demand. These are not factored loads. And you know that because dead load and live load. So I have to look at my 3 load combinations. 1.4 dead gives me 1.4 times 26.7, 37.4 kip feet. Or 1.2 dead and 1.6 live. 1.2 times the dead, 1.6 times the live, 102.8 kip feet, many times greater. Or you have 1.2 plus 0.2 SDS dead plus 1.0 live and 0.2, 1.45. This equals 84. So 37 102, 84, the 102 is going to clearly control.
So I just have a quick question. You may have one over it. So these are the factor of loads we always use, like the demand factor of loads we always use.
Yes.
What if there was snow or there was an earthquake or there was?
Yeah. Okay. Just to clarify, you're absolutely right. To clarify, what I'm saying is, for this class, for the purposes of this class, I gotta keep this within the scope of what I hope to achieve in the 10 weeks that we have. So I'm leaving wind and seismic out. I'm leaving snow out. I'm leaving rain out. I'm leaving icy wind out. I got to keep it within a scope of something that we can do.
Okay, so whenever you ask for the factor load demand, these are the three we're always calculating and deciding which one controls.
That is exactly right. But please don't forget, in the real world, you got to check all 7.
Okay.
Yeah, in the real world, there's no limitations. You might have snow, you might have earthquakes. You never know.
Right.
Right. But for the purposes of the class, I'm keeping it to just these 3. And I'll do you one better. If I give you a problem and I tell you that M sub u is equal to something, then I've already done this for you. You don't need to worry about this. If I give you M sub u, then you don't need to worry about this at all. You just run with what I gave you. But if I give you dead load, live load, or any other component, then I am looking for you to calculate which one controls.
Right, okay.
Okay?
Okay.
All right, so this is my factor demand. So now I'm going to calculate what my R sub n factor is. And I just plug in the 102. This is kip feet, so I put a 12-inch in here. Because my width and depth are in inches, so I want everything in inches, so always remember to put the 12 in there. Over 0.9 is my phi. Phi, as we just talked about, could be anywhere from 0.85, 0.86 to 0.9. We're not going to worry about that. We're never going to assume that phi is something less than 0.9, because that's not how you would normally design. So don't worry about that complication. Just plug in 0.9. The width of the beam is 9, and D is the depth through the steel, 16. Don't forget to square, and you get 0.595 KSI, or of course 595 PSI. So then to find rho, I take this value, plug it in here. I put in my concrete, my steel, concrete, and I get a rho value of 0.1098. Or using table A.13, make sure you use the right table for 4,000 PSI concrete, 60 KSI steel. And from the table, I get 110, which is round up from this. So my steel required is rho times BD. So now I have a rho times B times D. I need 1.58 inches squared of steel by design. So I am going to go, you can go to your tables, you can just look up what the area of 1 bar is and divide by the number of bars. However you choose to get to your total, I'm going to choose 3 number 7s. 3 times 0.6 gives me 1.8 inches squared. Here's a point where you have to kind of stop and reflect for a second. You have to have some engineering judgment when you're choosing your steel. I could probably get closer to 1.58 by using 8 number 4 bars. 8 number 4 bars would give me 1.60. And you say, oh, that's a better choice. Well, 8 number 4s is very inefficient. You're putting a whole bunch of steel down here. It may not even fit in 9 inches. And it's just not a reasonable solution. By the same token, I could put in 1 number 14 bar. right smack in the middle. One number 14 bar would give me enough steel, but that's not a very good solution either. So really, it just takes a little while to develop what a reasonable solution is, but usually 3 to 5, maybe 6 bars, depending on how wide the beam is. Okay, so for this, I chose 3 number 7s. I got 1.8 inches squared. I check my minimum steel requirement. Whoops, I skipped ahead. Please note these steps. These steps will repeat themselves over and over and over. When you review this document, please don't fluff over these steps. These are always required. The minimum steel comes from our equation. I presented this in the earlier lecture, where it is the larger of 3 square root f prime c over fy bwd, or 200 over fy bwd. So I plug into this my values. I get 0.455 inches squared. 200 over fy gives me 0.48 inches squared. Clearly this one controls, but my proposed solution of 3 number 7s is more than 0.48 inches squared, so I'm okay. This is my minimum steel check. Check ACI 318 maximum steel check. I got a lot of questions about this on the homework, so here's what we do. You have to calculate what epsilon sub t is equal to. So to do that, we calculate A. A is ASFY over 0.85 F prime CB. Again, this was in a previous lecture. This plug in all my numbers, 1.8, 60, 4, and 9. And I get 3.53 inches. With F prime C equal to 4,000 PSI, beta 1 equals 0.85. So C is A over beta 1, 3.53 over 0.85. I get C equal to 4.15 inches. Epsilon sub t is 0.003 D minus C over C. Again, all of these were presented in the earlier lecture. I plug in 16, 4.15, and I get 00857. Because 00857 is greater than 005, I know this beam is under reinforced, number 1. I know it is tension controlled, number 2. And I know phi is going to be equal to 0.9, number 3. So this right here, everything you see right here is my maximum steel check. Now, last step. Just because you're providing more steel than the equation or the table told you does not guarantee that you have sufficient capacity. You always have to check it. So my equation for a singly reinforced rectangular beam is phi ASFY D minus ASFY 1.7 F prime CB. I plug in all the pertinent values. I get 1384 kip inches because everything in this is inches. Divide by 12 to get 115.3 kip feet. And finally, phi Mn is equal to 115.3 kip feet, greater than 102.8 kip feet was my demand, so my design is acceptable. Okay, any questions on example number 1?
Professor, can you go back to the previous slide real quick? Sorry. No, stop, right.
I'm not doing it.
This slide. Okay, so that, okay, keep going. It was where you said AS min, that the check.
Yes, right there.
Okay, which one of these do you pick?
The greater.
Why the greater? Shouldn't
Because
you pick the smaller if it's asking for the min? I don't quite get.
No. It's asking for a minimum steel requirement. So whichever one is greater tells you the minimum steel you have to provide. Look at the numbers.
Okay.
Okay, if I'm looking for the minimum steel, am I going to provide 0.46 or 0.48? This is a minimum. So it is the greater of the two.
Okay. Okay.
Okay. And
Okay.
you can it's in the textbook and it's in the
That's
ACI
code?
code as well. And
Okay.
it's clearly defined as the greater of A or B.
Okay. Thank you.
Okay. Any other questions on example one?
Okay, Professor, for the previous page, when you used 0.9 to calculate the RN,
Yes,
we haven't got the E of T yet to
that's right.
check. Yeah, so do we just estimate that it's 0.9 at that moment?
Yes, that's what I was saying.
Okay,
Always assume at this early stage of the design, you always assume 0.9. You don't anticipate that you're going to be in that weird little transition zone. You always anticipate that you're going to be well and above 0.005. And then if you go through all this, that's why we do this final. You go all the way down to here. Oop, went too far, didn't I? Right there. That's one of the reasons why we always do this last step. If you found that epsilon sub t after all that was less than 0.005, so phi is something less than 0.9, then that would wash out right here and you would see whether it's okay or not. And if it's not okay, then you need to go back to step one and choose a bit more steel. But yeah, to answer your question, for R sub n, always assume 0.9.
got it. Thank you so much.
Okay. Any other questions on example one?
Yes, can you just go over again one more time with the checkout for the epsilon sub t? Why do you go with why is it that that's an acceptable value?
Right here?
Yes.
Okay, because it's an inverse relationship to the area of steel. Now remember from the last lecture, we talked about over-reinforced. If you have too much steel, then it forces the neutral axis too low on the beam and the steel won't yield. That's very, very dangerous. You could have a beam where the concrete crushes, but the steel had not yielded yet. And it's a very sudden and explosive failure. We cannot allow that. So the way that we make sure that we're not doing that is epsilon sub t. So the higher epsilon sub t is, the smaller A is becoming and the smaller the steel is. Or let me say it the reverse way. The more steel you put in here, the deeper A has to be, the smaller epsilon sub t is going to be. And if you have too much steel, then epsilon sub t will be too small. So we always check maximum steel by checking epsilon sub t and making sure that it is greater than 0.005 or 0.004 with some penalty. Does that help?
Yes, so you're making sure the strain in the concrete is greater than the steel than that of the steel.
No, I'm
Or
making sure
the opposite of that.
the opposite.
All right,
Yes.
then yeah, I got it.
Okay. Okay. All right. We're a little tardy for taking a little break. I got to get some more drink so I can make it through to the end of this. Why don't we reconvene at say 6:15? How's that?
Perfect.
Okay. So I will be back. We'll start example number 2 at 6:15. Okay, everybody, I'm back. Okay, so we left off starting example number 2. Okay, so example number 2 is going to be a design beam where the depth of the beam and the steel area are not known. So we have 2 unknowns in this case. Area steel is not known, and how deep is the beam. This is an example of how I'm going to do this in the future. If you see just M sub U equal to 900 kip feet, and you can assume that includes the beam self-weight, so there's no further factoring required. I've already given you the factored load. F prime C is 6,000 PSI. Fy, we're going to use 80 KSI steel for this guy. And our solution. Since the area of steel and the effective depth are unknown, we're going to shoot for a target epsilon sub t greater than or equal to 0.0075 to guide the design solution. Now, and keep in mind that design is just that. It's a design. It takes some engineering judgment, it takes some intuition, and sometimes it takes some trial and error to get the design to be optimal. So it's called design for a reason. There's no one single equation that will give you a perfect design. But since we're going to use this as our target, epsilon sub t greater than 0.0075, then we need to use that target to find what the d should be. So I'm going to use what we used before, similar triangles, where epsilon sub t plus the strain in the concrete, epsilon cu over d, is equal to epsilon cu over c. If you guys remember, I just draw this real quick. So the strain diagram, this is the strain in the concrete. Epsilon sub t is right here. This distance is d, and this distance is little c. So that's where this comes from. Oh, I cracked myself up. And there's what I just drew. So we use similar triangles. D is to the steel, C is to the neutral axis, and we're looking for epsilon sub t. So I just rearrange this and I plug in my values. I want epsilon sub t to be 0.0075, so I plug that in here. And what I get is C over D is going to be 0.286 from this relationship. A is equal to C over beta 1. So A over D is going to be 0.286 beta 1. I just took this and plugged it back into here. And so A is equal to ASFY 0.85 F prime C B. This is from before. And rho is equal to AS over BD. That's the definition of rho. And so then I can take rho, plug it back into here, and A is equal to rho FYD over 0.85 F prime C, which is equal to 0.286 beta 1 D. So now I can express rho as a function of F prime C, Fy, beta 1. Beta 1, again, we have 6,000 PSI concrete, so beta 1 is equal to 0.5, 6,000 minus 4,000 is 0.75. And of course, you can look at your table. I think it was 8.7, also gives you your beta 1 factor. So now I can plug everything back into my equation for rho, and I get a row required of 0, 1, 3, 6, 7. Now with a target row found, we now need to find a desired D value. So Rn is mu over phi bd squared, which is equal to rho Fy 1 minus 0.59 rho Fy over F prime C. This is a relationship we just went over. And I can take this relationship and I can plug in my rho Fy F prime C. And I get that Rn is equal to 0.976 KSI. You see where we're going with this? I know mu, I know phi, I know b, and now I know Rn, I can just solve for D. So D is equal to the square root of mu over phi b Rn, and I can plug in 900 kip feet, convert it to inches, over 0.918, 0.976 KSI, and I get 26.14 inches is my minimum D. Now, what would happen if I provide a D less than 26.14 inches? Will the beam work?
No, because it's below the minimum.
Actually, what would happen if I provide a D less than this value, then what's going to happen is the smaller D gets, the more steel I need to make up for the lack of leverage. So I can still make it work. I just have to put more steel in there to make up for the lack of distance. But if I put in more steel, then epsilon sub t is going to go down. So what's going to happen is if I don't provide at least this much D, then I'm not going to hit my target of epsilon sub t being at least 0.0075. That's what would happen. So therefore, the minimum D is 12.14, and really in order to hit epsilon sub t 0.0075. Adding 2.5 inches for the minimum height, I get 26.14 plus 2.5 is equal to 28.64 inches. I am not going to ask the construction company to build me a beam that is 28.64 inches high. I'm going to choose 30 inches. I'm going to round up. I don't round down because D and D would be less than what I want. So I'm going to round up. So with a height of 30 inches, that's something I can build. Then I find what my real D is going to be, 30 inches minus 2.5 inches, 27.5. So this D was my target minimum, but this D is what I'm actually going to build. Does that make sense to everybody?
Professor,
Could
why
you
should you?
repeat-
Oh, my, go ahead,
ahead.
go ahead. Is it okay? Why did we pick 2.5? It wasn't the cover supposed to be like 1.5 for minimum?
Good question. The coverage is 1.5 as a minimum. Yes, what you just said, absolutely right. But that coverage is to the outside of the ties. The ties are assumed to be a 1/2 inch in diameter. So that gets you to 2 inches. And then you got to go halfway up the bar to get to the center of the bar. So that's why, roughly speaking, it's 2.5 inches from the bottom of the beam to the center of the bar.
Oh, okay, makes sense. Thank you.
Ahmad, you had a question?
I just wanted to repeat this part, but then you just explained it like while answering his question.
Okay. Okay. All right. So now we have a rho minimum and we have a D that we're looking for. We can solve for the required steel. AS required is rho BD. I now have a D, B was given, and I solve for rho. So now I just plug them in. 0.01367 times 18 times 26.14. This is the minimum. I'm plugging in. And that gives me 6.43 inches squared. Now, why did I use the minimum and not the D that I'm actually using? Well, because the minimum came from the load. And the D that we're going to use came from the actual physical constraints of building the beam. So if I put 27.5 in here, and I'm still using the original row that I got here from the actual load, then I would have overestimated how much steel I need. So I'm keeping it apples to apples. The minimum D that I solved for, the minimum row that I solved for, defined the minimum area of steel. So that's why I use this one, not that one. If you plugged in 27.5, it's not horribly wrong. You're just overestimating a little bit.
Professor, so are we telling the contractor to 27.5 in this case, or 30?
We are telling the contractor to build the beam 30,
Okay.
but that's the bottom of the beam to the top of the beam. And then we're going to tell the contractor that I want the steel to be 2.5 inches up from the bottom of the beam, thus giving me D of 27.5.
Right. All right.
Okay? All right, so I have a minimum area steel that I have found, 6.43. Now I need to choose steel that will give me 6.43. So I'm going to choose 6 number 10s. And I chose 6 number 10s because 6 times 1.27 is 7.62 inches squared, more than 6.43. 6 number 9s would have given me 6 square inches. That wouldn't work. And there's all kinds of combinations that you could use, but this seemed to be the most workable. I'm going to check the minimum width. And from table 8.5, which I'm going to use from now on because doing it by hand is cumbersome, beam minimum is 17.95, and I've got an 18-inch beam. So I barely squeaked by. If this did not work, if the minimum width is wider than what I'm looking for, I only have 2 options. Option number 1 is to use fewer but bigger bars. Maybe 5 number 11s would do it. I'm not sure, but that's one option. The other option is, and if fewer bigger bars doesn't do the job, then the only other option you can have is to put all your steel in multiple rows. So instead of it having all in one row, you have to put it in multiple rows. That's fine. When you have to do that, that's fine. But remember, you have to refigure out how deep the beam has to be. Because if you put all your steel in 2 rows, then you are no longer going to be 2.5 inches to the center of your steel. It's going to be more. So you kind of have to back up a little bit. Okay?
Professor, did you use number 3 or number 4 for the table 8.5, since we don't know what the ties are? The ties aren't given in this problem.
Good question. With number 10 bar, I could use a number 3. I don't remember. Let me, okay, table 8.5.
Use the number 3.
I did use a number 3. Yes. 6 number 10s is 17.95 with the number 3. With a number 4, I would have needed 18.7. So there you go. I use number 3s.
Professor, I have a question. How did you choose the 6 number 10s? I'm confused there.
Well, I needed an area of steel that equals 6.43.
Right.
And I needed to choose a number of bars that would fit in 18 inches.
Right.
So I kind of just, through my mind, went through the different combinations that might have got me there, right?
Okay.
So if I started with, say, number 8, let's just go through this for a second. If I tried number 8 bars, 6.43 divided by 0.79 means I would have needed It's 8.14, so I need 9 number 8s. So I go to my table and I look at 9 number 8s. Is really not very reasonable, but it's 15.25 plus 3 times 2 is 6. That would have been 21 inches. Okay, so that's not going to work. All right, so how about number 9s? 6.43 divided by 1 inch is 6.43 bars, so I need 7 number 9s. Number 9 is 16.53 plus 2.26 equals 18.79. That doesn't work. Okay, so then I got to 6 number 10s. That does work. Or I could have said 6.43 divided by 1.56 would mean I need 5 number 11s. And 5 number 11s does fit. So I could have used 6 number 10s, or I could have used 5 number 11s.
Okay.
Does that help? Okay,
Yeah.
I have another question that said, if I went to 2 rows, wouldn't that change your D if you use 2 rows? No, it doesn't change D because I calculated what my D needs to be. But what it does change is the height of the beam. So I would have used 26.14, and if I knew I had 2 rows, I would have added another inch here. So that would have been plus 3.5, which would have been 29.64. I still would have used 30.
Professor, why do you add an inch? Isn't it half an inch? Because the difference between them is an inch, and the D we find is in the middle of them. Isn't it half an inch?
Yes, but you're forgetting the other half of the rebar,
Oh yeah, my bad. Yes.
right? You got half a
Okay.
rebar diameter plus a ½ inch. So
Okay,
that's
makes sense.
about an inch. Okay. All right. So this takes a little practice. Granted, I've been doing this a little bit longer, so I kind of have an idea what fits and what doesn't. But yeah, this takes a little practice. And again, if you find that no combination will possibly fit in the beam that you have, then you have to go to 2 rows. And if you have to go to 2 rows, you just go back up to here and start over and from this point. And you calculate what H is, and then from H you calculate what your D is, and then you come to a solution. Okay, but luckily for us, 6 number 10s does fit in 18 inches. I'm going to check my minimum steel requirement, and I have equation 1 or 2, and equation 1 gives me 1.44 inches squared. Equation 2 gives me 1.24, so equation 1 controls, and 1.44 is far less than 7.62, so no problem with minimum steel. But we still have to do this check. Check a maximum steel. Maximum steel, I need to calculate epsilon sub t. So to do that, I calculate A, and we get 6.62 inches. Beta 1 is 0.75, so C is A over beta 1, which is 8.83 inches. So epsilon sub t, I drop in D and C. Now here, I'm calculating epsilon sub t. I have to use the real D that I'm actually going to build. If the real D is different than your minimum D, don't use your minimum D, use what you're actually building. Because your epsilon sub t, you're checking what you're actually going to build. And epsilon sub t is 0.0634. 634 is greater than 0.005, so we are perfectly okay, and our phi factor is 0.9. That's our maximum steel check. Last step, always recheck your assumed steel for capacity. So here's my equation for singly reinforced beams. I plug in, now here, you have to plug in what you're actually providing in steel, not the minimum required, but what you're providing. So 7.6 inches squared, 80 KSI, my real D, 7.6 times 80 KSI, concrete is 6, beam is 18 wide. I get 13,236 or 1,103 kip feet. 1103 is greater than 900, so my design is acceptable. This is the only thing that really, really matters. All of your techniques to come up with a D or a rho or area of steel, guesstimates, and by gollies, none of that really matters until you prove it right here. Okay? I say that over and over because inevitably, somebody is going to say, I need 6.4243. I'm giving you 7.62, so therefore the beam's okay, and they go on to the next problem. They have missed the minimum steel requirement. They have missed the maximum steel check, and they have missed that phi min is greater than mu. Okay, so in my book, they missed most of the problem. I want to make sure everybody's very, very clear about this. If you don't do your minimum steel check, you don't do your maximum steel check, and you don't do your capacity check, you've missed most of the problem. Any questions?
Professor,
Yes.
for the literally the second line up, isn't that supposed to be 7.62?
Do I have a typo? Probably.
Because, yeah, it's our AS on the top one, it says 7.62, that's why.
6 times 1 point. Yeah. Yep. Typometic. Okay. Thank
And
you
you
very
also
much.
have it throughout the rest of that problem.
I'm sorry, Ashley, what was that?
You also have it throughout the rest of that problem too. You carried it through.
The 7.60?
Yeah.
Okay. All right.
And then, Professor, when do we know that we have to use 2 rows of steel?
When it won't fit in one row.
I know, but is there like a way to know that it won't fit?
Yes. Just a second.
Okay.
7.60 inches squared AS. It's supposed to be 7.62, you said?
Yes.
Okay, we'll fix that. All right. As I had just explained, if you go through every possible combination of steel, 9 number 8s, 6 number 9 or 7 number 9s, 6 number 10s, 5 number 11s, you've gone through every combination of steel that gives you as much or more than what you need. And none of those combinations fit within the width you need it to fit in. According to table 8.5, then you must go to 2 rows.
Okay, got it. Thank you.
Okay. Okay, example number 3. Design a beam where the depth, the width, and the steel are not known. So now we don't know much. What we know is we need to carry 800 kip feet a moment. And what we know is we have 5,000 PSI concrete and 60 KSI steel. Solution. Okay, so we need some guidance on this. Or otherwise, think of it this way. If I didn't give you guidance, then with 32 people in this class, we would have 32 completely different answers. And they could all be correct because there's an infinite number of combinations to achieve 800 kip feet of capacity with different values for B and D. So we need something to guide the solution. In this case, we're going to ask that the B is equal to or less than half of D. That's the rough proportions that we want. And we want epsilon sub t to be greater than or equal to 0.0075. Those are our targets. From table 8.7 for grade 60 rebar and F prime C equals 5,000, rho is 0.0162. I should add at epsilon sub t equal to 0.0075. Okay, so if you have your textbooks, and you go to table A.7, you have a matrix here, and you go over until you get to the 5,000 PSI column. You go down until you get to the grade 60 rows, and then the rows are labeled row balance, row when epsilon sub t is 004, epsilon t is 005, epsilon t is 0075, or epsilon minimum. Those are the various rows under the grade 60. You go to epsilon sub t equal to 0075 for 5,000 PSI concrete, and the number that's right there, 0.0162. That's how we get this number.
So I just have a question. Are we always using the 60 rebar?
No, last example we used 80.
Okay. Is it going to be given or?
Yes,
Okay.
yes. Yeah, I got to do the class so that we don't have 32 different answers for everything.
Right. Yeah, because like I was looking at the top given, it wasn't there. So you're giving it us here, like with the.
Okay. No, I now get your question, and that's a good question. I did the last example using 80 KSI so that you can't use the tables. And if you can't use the tables, then you have to use the relationship between R sub n and rho. That's why I used 80 KSI in the last example. It forces you to use the equations instead of the tables.
Oh, okay, right.
Okay, but
Right.
this one I made 5,060 so that you
Right.
can use the tables, and you
Okay.
can see how much quicker it goes with the tables. Okay?
Yeah.
Okay. So with a target rho found, we now need to find a desired value for D. So again, we use Rn is equal to mu or phi BD squared, which is equal to this expression with rho and Fy. And I can plug in rho. I have Fy, and rho Fy F prime C. And I have Rn, R sub n is equal to 0.861 KSI. And I can relate that to mu over phi BD squared, which is also if B is half of D, I can put then D over 2. So now I have 2 mu over phi D cubed, and I can solve for D. D is the cube root of 2 mu over phi Rn. Now I can plug in all my numbers. Don't forget the 12 to go from feet to inches. And I get a D of 29.15 inches. This is my target D, or D minimum. So D minimum is 25.15. So B minimum is half of that, 14.58 inches. Adding 2.5 inches for a minimum height, my minimum height is 31.65 inches. I can't build 31.65 inches, so I'm going to call it 32 inches. With H at 32, then D is 32 minus 2.5, 29.5. And with D at 29.5, I'm going to try a B equal to 16. It's not less than or equal to half of D, I understand, but it's a nice round number. So remember, these are targets, and this are kind of converging on a solution. So with D at 29.5, B at 16, and rho at 0.162, I can solve for my required steel. Now again, for required steel, I plug in my minimums, 29.15, 14.58. I plug those in to find the steel. So AS required is 0.0162, 29.15, 14.58. I need 6.89 inches squared of steel. I'm going to choose 6 number 10s again. 7.62 inches squared. Per the table, 17.95 is greater than 16 inches. Uh-oh. No good. So what I'm going to do, I'm going to cheat. That's right. I'm going to cheat. And I'm going to adjust the width to 18 inches. Remember, these widths are generally modules of 2 or 3 inches. So I'm not going to use 15. I'm not going to use 17. I'm going to go from 16 to 18. And 18 will fit my 6 number 10s. So now that I have, and you can see there's kind of a little bit of an iteration process, but now that I have a design steel, design D, and design B, I can now go and find my minimum steel or check my minimum steel requirement. Is the larger of the two. I plug in my values, and these are my design values. I don't use my minimums anymore. I use what I'm actually building. And I need 1.88, or I need 1.77, 1.88 controls. 7.62 is greater than 188, so we're okay. Check my maximum steel. Going through the same exercise, and there's the same problem. Let me write that down real quick. Slide 293. Okay, and I need 5.96. Beta is equal to 0.80 from the table. So C is equal to 7.45 inches. And epsilon sub T, I plug in my actual D and the C, 29.5, 7.45. I have 0.888, which is good. It's greater than 0.005, so phi is equal to 0.9. Now remember, our target was 0.075. Why am I off my target? Anybody?
Is it because you adjusted the width?
It is. It's because I adjusted the width, and it's also because the minimum depth that I needed, I can't build. I rounded it up to the nearest height that I can actually build, and then found the right D based on the height. So that was just a target to get started. But because I need to build the beam in even modules, the D actually ended up being quite a bit more than my minimum D. So epsilon sub T got better. And I have a question about beta. Let me check my beta. The easiest way to check beta is just go to table 8.7 on page 598. And I am using 5,000 PSI concrete. So beta is 0.8, 0.80. Okay, so you can check that for yourself, that beta is 0.85 for 4,000 or lower, 5,000 is 0.8, 6,000 is 0.75, and so on until you get to 0.65. Okay, what's my last step? Always, always, always recheck assumed steel for capacity. And remember what I said earlier, this equation, you keep seeing the same equation over and over, which is fine, but just remember that this is only valid for singly reinforced rectangular beams. And we're not always going to have singly reinforced rectangular beams. Just remember that. But we do this time, so we can plug in the right steel. I got that same typo that persuaded through here, but this equals 10,884 kip inches, which is 907 kip feet. 907 kip feet is greater than 800 kip feet. Therefore, the design is acceptable. Okay, I am going to be a stickler on this one. Even this is not taking the problem far enough. You have not finished the problem. The problem is not finished until you do this line right there. And why? Why am I doing that? Because ultimately, What you need to prove to me is that phi mn is greater than mu. That is the only thing that matters. Other than you met the minimum steel and you're not exceeding the maximum steel. Yeah, that stuff's important too. But if you haven't demonstrated that you're providing a beam that has the necessary capacity, then you haven't done your job. You're not done. So taking it to even this point right here, which may in your mind be stating the obvious, is not obvious enough. I want phi mn is greater than mu. So 907 is greater than 800. Now we are done and we can move on. Any questions about example 3? Okay. Example number 4. Here we design a beam where the depth, the width, and the steel area are not known. This time the factored moment is 1500 kip feet. F prime C is 4000 psi and my steel is 60 ksi. My solution, I want B to be equal to or less than half a D, and epsilon sub T is targeting 0075 again. From the table, A7 for grade 60 rebar and F prime C equal 4000, at 0075, rho will be 0.0138. Now with the target, we now need to find our desired D value. And we run through the same exercise as we did before. We plug in rho, Fy, rho, Fy, F prime C. We get 747 KSI. Rho is equal to mu over phi BD squared, which is mu over phi D over 2 D squared, because we're shooting for B is equal to half a D. And so again, D is the cube root of 2 mu over phi Rn. I can plug in my values, don't forget the 12, and I get a D required of 37.69. Therefore, my minimum D is 37.69. My B minimum is 18.85 inches. Adding 2.5 for the minimum height, I get 40.19 inches. With 40.19, I'm going to choose H equal to 40. It's so close. Let's see if we can make it work. With H equal 40, D is equal to 40 minus 2.5, 37.5. With 37.5, I'm going to try B equal to 20.
Sir, I just have a question. I'm very sorry.
Yeah.
So we have the first D that's equal to 37.69, right?
Mm-hmm.
And then the second D is 37.5.
Yes.
What's the difference between these two Ds?
This is the one that we got from the theoretical equivalent.
Right.
So basically what we fed into the machine is the desired capacity here and our target rho, which corresponds to epsilon sub T of 0.75.
Right.
So this target gave us a rho, and this demand fed into here, that gave us a target D. In this case, I'm proposing to provide a D that is slightly smaller than my D minimum. And is that going to be okay? I think it's going to be okay because B is actually a little bit bigger. And this was just a target. If I undershoot this by a little bit, it's still going to be okay.
Right. And for B, we're just taking half of this number, or?
Well, our target was B is equal to half a D.
D. Right.
But half a D, half of 37.5 is a weird number. So I rounded it up to 20.
Okay. But in our continuing calculations, we go back and use the D we found through our theoretical calculations?
Yes, because remember that a rho was based on assumptions.
Right.
And D was based on the same assumption. B was based on the same assumption. So I'm using all three of my original design values because those were based on the 0075 and a capacity of 1500.
Okay.
So I'm going to plug those into here, and I'm going to get 9.8 inches squared. So choose 10 number 9s, which gives you 10 square inches of steel, which is really close to 9.8. Per table 8.5, B minimum is 25.57, which is greater than 20. So I could do one of two things. I could say, all right, let's make the beam 26 inches wide. But that's getting a little excessive. So to be more efficient, there just is no solution to get 10 square inches of steel that will fit in 20 inches wide. So we need to put them in 2 rows. And this answers the other student's question. When do I know that I need 2 rows? Well, I can't fit it all in what I've got with any combination. So if you look through the charts and try to make it work with number 8s, number 9s, number 10s, 11s, 14s, nothing is going to fit in 20 inches. So I have to use 2 rows. So I add, yes?
I'm looking at the table 8.5. I don't find that B min of 25.57. If it's
Okay.
so that comes from the ties, number of ties, right?
Okay, well, let's see. I'm proposing 10 number 9s.
Right.
Okay, so what you do is, I think I'm figuring number 3s. So you have 6 number 9s is 16.53. You see that?
Right.
Okay, so 16.53 plus I need 4 more number 9s. So at the far right, it says add for each additional bar 2.26. So I go 4 times 2.26 equals 25.57.
Oh, I see.
Okay?
Uh,
And I'm glad you asked that question because I'm sure somebody else had the same question.
you said 6 bars?
No, 10 number 9s.
Yeah, 10 number 9s. But you're looking at ties. You're looking at a number of bars in a single layer.
Yes. So if I try to put all 10 number 9s in one row, it would be 16.53
Yeah.
plus 2.26 times 4.
Yeah. Okay, I see.
You see it?
Yeah. Yeah. I
Okay.
see. Thanks.
Okay. So I need 2 rows. So I'm going to add 2.5 plus 2 inches for the minimum height to my H minimum. So now I'm going to go with 4.5 inches, which gives me the 42.19. And it's so close again. I'm sticking with my 42. So I'm going to calculate what my actual D is going to be. Okay, so please don't miss this. I know we're getting close to the end here, but don't miss this step. I chose 42 because it's a nice round number. It's an increment of 2 inches. And I know that somebody can build a beam 42 inches deep. So I chose 42. But with that, I'm going to calculate what my actual D is. My D is going to be the 42 inches minus 2.5 inches to the center of the first row minus my bar diameter over 2, because the center of the first row is to the center. I still got the other half of the bar, plus the 1/2 inch. That's the minimum space between the 2 rows is 1 inch. So I go 1/2 inch to get to the centroid of the steel. And that equals 38.44 inches. Okay, and I've drawn it for you. I need 10 number 9s. So they're in 2 rows of 5. I'm 2.5 inches to the center of the first row, but I still got to go the other half of the bar and then half of the 1 inch space. And that gives me 38.44. There is no need to round up or down 38.44. That's what they're going to build. I rounded up the overall height of the beam and the overall width of the beam to something that can be formed, but the D is what it is. So you don't need to mess with this number. That's your number, 38.44. Okay, now I do my checks. We're running out of time, so I'm going to go through this real kind of quickly. These are the same minimum checks we've done before, and my minimum is 2.56 inches squared. 10 inches squared is clearly much more than 2.56, so minimum steel is satisfied. I check my maximum steel. I find AS, I plug in my actual area steel, the yield, and I get 8.82 inches. For 4,000 PSI concrete, beta 1 is 0.85. So C is 8.82 over 0.85 is 10.38 inches. I calculate epsilon sub T. I plug in D and C. There's my 38.44. Again, no need to round this one up. It is what it is. C is 10.38. I get 00811, which, by the way, is pretty darn close to my target of 0.75. It's greater than 005, so phi is equal to 0.9. So my last step is always check my capacity. I plug in my 10 square inches, 60 KSI, 3844, and I get 18,375, which is 1531 kip feet. Last step, 1531 kip feet is greater than 1500 kip feet, so my design is acceptable. And that is the end of our presentation. Do we have any questions?
Professor, so
Yes.
whenever we're checking the B minimum, do we always use number 3 stirrups or ties?
Two answers to that. If the problem statement says that we're using number 4s or even number 5 ties, then follow what the problem statement says. The second answer to that is, if you are using number 11s or bigger, you need to go to number 4 ties. But I think maybe the better answer for your purposes is, if I don't tell you nothing, then just assume we're using number 3s. Any other questions?
Thank you. Got it.
Okay. Anybody else?
Not yet.
Okay, that's a good answer. So this was a pretty meaty one. If you have questions, we'll start off our next lecture with a little time that you can ask some questions about this lecture. I am not worried if we don't finish every lecture every time. And I happen to know that the next presentation I put together, it actually has a lot more slides than this one. And this one was kind of a race to the finish one, isn't it? So I've got this whole thing built in that sooner or later, we're not going to get to the end of a presentation. We'll pick it up the next time, and that's perfectly fine. And I want that to be clear to everybody so that at the beginning or anytime during the presentation, feel free to ask your questions. You can see how this design thing is like a snowball. It just keeps building and building and building. If you're not up to speed on how I got, where was it, right here? Okay, if you're not up to speed of how I got little a or beta 1 or C, then pretty soon you're going to be lost on how I get to epsilon sub T. So I want to take the time and answer questions and make sure that you're on solid footing as we go from rectangular beams to T-beams to doubly reinforced and so on and so forth, okay? So we're out of time today, but have your questions ready. homework assignment number 2 has been posted, so you can start working on that. I will try to post the solutions to homework number 1 sometime tomorrow. And I will also post this lecture to YouTube, hopefully tomorrow as well. So if nobody has any further questions, I will close our time. And we'll see you next time.
Thank you, Professor. Have a great day.
You too. Thank you.
It's the only one.
Have a good one.